Okay, ladies and gentlemen, great to see you back for our public lecture series on sustainability in computer science. Today, it's kind of a premiere that I welcome Stefan Nastic, Professor Stefan Nastic. I think last time there was a flu involved, which that it was not possible to have you. This is a very interesting topic. You are talking about, how to this is now really sustainable computer science, how to build the next generation of, a computing landscape in a more sustainable way. Yeah, we just today had a discussion of, will the data centers use less energy in the future? So perhaps we can ask you this at the very end. But without too much further ado, Stefan, it's your floor, and thank you that you're a guest in our lecture series.
Perfect. Thank you very much for a nice introduction, Gertie. I hope you can see my screen and everything looks as it should. Okay. I will then start. And by the way, I also have a slide or at least one graph on the data center energy consumption. So we'll get to that as well. So welcome everyone. Good evening and welcome to my lecture. And today I will be talking about emerging paradigms for a sustainable next generation computing landscape. So there is a mouthful, but I want to start first with kind of a general overview of things. And as you probably know, distributed systems and in general distributed computing has been a backbone of modern life and the key to the modern society for many years now. And systems such as smart cities, autonomous vehicles, healthcare, disaster recovery, and so on largely depend on some form of distributed compute infrastructure or distributed computing in general to function properly. And here in the first figure, so on the right-hand side, we can see this 10,000-foot overview of this computing landscape and how it consists of multiple domains, but also multiple infrastructures and systems which kind of converge together in order to provide this compute landscape. And while these computing systems are rapidly evolving, we still face many, I would say, fundamental challenges which are crucial to our society, such as performance, reliability, and scalability of these systems, but also dealing with cost effectiveness, energy efficiency, CO2 emission, and also what Kathy just mentioned, computing or computational sustainability. So all of these goals really need to be addressed somehow if we want to achieve this next stage or this kind of next generation computing systems and compute landscapes, right? And now, if we zoom into this compute infrastructure, we will find well-known domains, as we already mentioned, such as cloud, fog domain, edge domain, IoT, and so on. So if we look at the far left-hand side, there we have many smaller end devices or IoT devices, which display certain properties, such as that they have limited compute power, they have relatively low reliability, they are rather volatile, they also have very limited energy consumption in a sense, they're battery powered and they don't consume as much energy, and they are also generate much less CO2 compared to the other layers based on that fact. And this is true at least in terms of scope 1 emissions. And then as we move to the right-hand side, we have the edge devices, so the kind of the edge of the network, and things are slightly changing there, right? Because there we find more general purpose devices, right, which are have some redundancy, hence they're more reliable, and on top of that they have low latency to the end devices. However, they do now have a higher energy profile, but also higher cost profile. So we already start to see a pattern forming here in terms of we are sacrificing some properties, but we are gaining some other properties. And then as we move further into the core network, this is not really, this is kind of the communication network, right? The internet backbone, if you will, included with the additional core network. This is not the main focus of today's talk. However, it's worth mentioning that this is not really these resources aren't really tapped into as much, meaning that these are mainly controlled by the telcos and they're still not used for general purpose computing. Although this is changing with the emergence of 5G, 6G, and so on, right? But yeah, anyway, moving into the cloud domain. So there we have these very large data centers, right? And they kind of have theoretically unlimited compute and storage resources, right? At the same time, they also have high availability. They do offer kind of a lower cost, but at the same time, they are consuming much more energy. They are emitting much more CO2, and in general, cost of now operating the entire infrastructure is obviously much higher. So from the macro perspective, if you will. So what we can see here is that performing computation in this so-called edge cloud continuum requires us really to constantly make various trade-offs regarding the compute power, latency, cost efficiency, reliability, and sustainability of the computing. Now, recently, what we have seen is the new class of computing infrastructures which have been emerging. And these are so-called in-orbit constellations, right? And they're mainly comprised of LEO or lower Earth orbit satellites. And these are the satellites which have the average cruising altitude of between 500 and 2,000 kilometers. And typically, these satellites are arranged in planes, so kind of parallel planes, which are evenly spaced around the Earth. And then you can view this one plane kind of as one road, so to say, where multiple satellites are then orbiting, right, one behind another. And for example, in the figure on the right-hand side, we can see the phase one of Starlink constellation, which has been developed by SpaceX, right? And this is as I said, phase one, the initial phase with 24 planes and 66 satellites each, right, in each one of the planes. And this is the so-called main shell, determined based on the inclination of satellites to the equatorial plane. And so the first phase had some 1,500 satellites, and currently we are already up to 7,000 satellites, and the plan is to roll out 30,000 satellites, which will be of the second generation. And this is only talking about SpaceX, right? And there are other providers, and this is very competitive and very hot, so to say, space. No pun intended there. And it's important to note that these satellites can perform some kind of local computation. And why is this important? Well, because they can then they can act as regular compute nodes, so similar to what we have seen previously in terms of our IoT devices, edge devices, large data centers, and so on and so forth. And typically these constellations, the satellites communicate with the core of the network. So how they connect to the rest of the edge cloud continuum is through the core of the network via some ground station, and the communication there happens via some kind of radio frequency. It's radio frequency based communication, and typically it's a K-band radio frequency, right? At the same time, they can communicate among each other, and this is typically done via ISLs or intersatellite links. And these you can view as a kind of laser antennas, which have a high speed and high bandwidth. And this is really high speed, high bandwidth, going up to 100 gigabytes or gigabits per second, right? But what's probably the most important is that these infrastructures provide really additional capabilities, such as global reach, coverage, Earth observation capabilities, low latency communication for remote regions, real-time global sensing, high resolution environment monitoring, and really across previously inaccessible geographies. However, again, we have a trade-off, and this time it comes in terms of cost effectiveness, because typically these infrastructures aren't really as cost effective because you need to, first of all, launch the satellites, which is very expensive, and also you need to have an entire constellation. Regardless how big or small, you require more than one satellite for all of these kind of capabilities to emerge and for this infrastructure to start making sense. And then finally, also these satellites aren't as powerful in terms of their computing power and compute capabilities, although recently we have seen also some accelerated servers like Jetsons, etc., appearing in these infrastructures. So what we have seen or what we have been experiencing is that all of these infrastructures, which we now mentioned, and this kind of compute landscape have been converging into something which I refer to as 3D compute continuum, right? And let's maybe first briefly discuss or define what continuum is. And it is a sequence in which adjacent elements are not perceptibly different from each other, but the extremes are quite distinct. And I think this is this should very nicely summarize, right, the infrastructure that we are dealing with. On the one hand side, you have small sensors, embedded devices. On the other hand, you have very large data centers, and then finally you have these satellites, right, which are definitely different from each other, so to say. So we can see that the 3D continuum is really a large pool of interconnected compute, network, and storage resources, which are distributed across all spatial dimensions, so to say, to kind of imagine the 3D space, Euclidean space. And it's important to note that these are usually hierarchically organized, logically layered, and globally heterogeneous. And we will come to this point of global heterogeneity of the infrastructure. But before that, I just want to look at some 3D compute continuum applications. Because they are really abundant, and they range from wildfire monitoring and recovery, marine lifetime monitoring, but also they help us deal with large-scale blackouts. And what we can see here at the bottom, this is the network consumption of in Spain during the big electricity blackout from last year. And you can see how the network relatively quickly was able to recover, largely thanks to the kind of 3D compute continuum in this sense, while the network connectivity was transferred from the ground connections to the satellites, specifically to SpaceX. And this is something which can be seen here, how the ground stations in Milano and Madrid are being kind of taking over from the Madrid ground stations. Moreover, there are many emerging use cases and techniques which are enabled by this 3D continuum, right? And these techniques have advancing sustainability as their kind of main focus. And for example, hyperspectral images is one of the Earth observation techniques where instead of recording just three color bands, so RGB, red, green, and blue, it measures hundreds of very narrow contiguous spectral bands for every pixel. And essentially what it enables us is to create this type of like a fingerprint, like a material fingerprint, and really that enables us to detect the the materials, right, from very large distances with very high precisions. And ESA aims to provide routine hyperspectral observations through the Copernicus program, which is in line with EU policies for natural resource management. And one of these missions is the CHIME mission, which advances sustainable practices for agriculture, biodiversity, soil, environmental prevention and preservation, and so on and so forth. And there are also many upcoming missions from ESA. And here I'm just showing some of these, images, how they look like. Here we can see the hyperspectral images of minerals. Then we can also see their application in agriculture, where they can be used to determine the quality of the soil, but also the quality and the health of the crops. But they're also used to manage to detect and monitor the quality of water, for example, in different environments. And in addition to that, I think the images looks very, very beautiful. Now, coming back to our definition of the 3D continuum, we see that it is comprised of a large number of heterogeneous devices. We said that already. And these devices have really, orders of magnitude differences in terms of their number, resources, device costs, their size, and so on and so forth. So we're moving from, very large number of small devices to fewer but very powerful devices, such as large data centers, for example. And this heterogeneity has kind of it's a two-phase thing, right? One of its inherent properties is that it affects many non-functional aspects of the infrastructure, such as enabling trade-offs in terms of cost effectiveness, reliability, performance, and so on. So it can be a good thing if we can exploit it properly. At the same time, managing this heterogeneity is something which poses a lot of challenges which need to be overcome in order to be able to capture the benefits of the 3D continuum, right? And this heterogeneity really goes also beyond the device heterogeneity to also include for example, geographical heterogeneity, where we have so-called different densities of the compute continuum. And this is typically expressed in terms of, number of devices which is collocated in one geographical region. So if you think about urban areas like cities, you can see that there are, many, many more of compute devices available there, as opposed to going to rural areas. But also there is this kind of global difference in the computing continuum density. And as you can see also on the bottom right-hand image, we have a map of AWS data centers, and how they are spread out throughout the world. And you can see that vast majority is kind of focused or present in the United States, Europe, and then also to a certain extent at the far east. It's also interesting to notice that there are these sporadic density shifts, meaning that, for example, the data production will significantly vary and increase when, let's say, some music festival happens or some large sports event or whatever, which attracts a lot of people who then in turn produce a lot of data and consume also a lot of compute, right? But again, this is not the end of it. We also are dealing with the software heterogeneity, or we have to deal with software heterogeneity and along multiple dimensions. So we have that in terms of programming languages which we use, for example, going from low-level programming languages to high-level programming languages such as Python. We also have various platforms which are present in this 3D compute continuum. And I'm just listing some of the well-known ones, such as hyperscalers like Google, AWS, but also more kind of edge native platforms such as Cloudflare, Fastly, and so on. Finally, there is also a significant difference or heterogeneity in terms of the application domains, where we have AI ML applications, autonomous vehicles, augmented reality, but also traditional applications, which can be, as we have seen also in part previously, which can be deployed on top of the compute continuum. Another challenge is that we face is the hypermobility of the compute infrastructure, right? And there are some mobility challenges also in traditional infrastructures. However, in 3D continuum, this is brought to a completely new level because the satellite motion is governed by orbital dynamics and it is not user-defined, right? And this results in a very high velocity, right, of satellites, which are cruising at some 28,000 kilometers per hour. They have a very dynamic coverage footprint. Essentially, you have only few minutes to communicate with the ground station because the satellites are flying very quickly above these ground stations. At the same time, they can only downlink only a limited amount of data, some 20 gigabytes, whereas they create and they can produce terabytes of data. If we talk, for example, about hyperspectral imaging and other techniques also. Then we also need to deal with physics, right, with the nature limitations, such as, the Doppler shift due to, again, high-speed relative motion, which leads to signal deterioration and can also affect the communication. And then finally, the satellites are not flying, so they are not cruising at these ideal orbits, but they are actually cruising along the perturbed Keplerian orbits, right, which deviate from this ideal two-body Keplerian trajectories, right? And then also, in addition to this, there is a growing energy demand of the compute infrastructure, right? And this is mainly driven recently, at least, by the explosion of the AI workloads. And we can note, for example, that training a large frontier model now requires tens to hundreds of megawatt hours per run. Which is quite a lot. And also the emission of CO2 emissions of training, a large transformer model, it's about 300 tons of CO2. And if we compare that to an average person, which only emits 5 tons of CO2 per year, we can see that, we are talking about really some serious scale, so to say here. And as you can see also on the images on the right-hand side, this is only projected to grow in the future. And this also now bringing us back to our initial discussion that data center electricity demands are already very high, so 1 to 2% of the global electricity today, and that is expected to double by the 2030. And this is also again enlarged due to this heterogeneous compute devices, specifically like accelerated servers, for example. Additionally, it's also interesting to note that it's not only compute, which requires a lot of energy, but also the data movement itself. So basically, data transfer are very, very heavy in terms of energy consumption. And that's why the application and systems are increasingly rely on the distributed edge cloud space pipelines. And what's important to note here is that the scalability of modern compute is increasingly bounded, not only by compute, but also by energy availability and energy efficiency. And in short, what this means is that the energy, and for this matter, the whole sustainability, is not longer a secondary concern, right? It is really becoming a limiting system resource, which really determines and shapes how we build these computing systems and also how we operate them. So we saw that the 3D continuum effectively provides a large pool of these interconnected resources which converge into a compute infrastructure, but are we able to compute everywhere without worrying about the underlying complexities of the infrastructure, such as we said, heterogeneity, density, mobility, energy consumption, and at the same time keeping our systems and application sustainable? Well, ideally, we should not have to worry about infrastructure when we deal with systems and applications which we are building, right? We should ideally consume them as utility. And a nice analogy there is simply if you're building, let's say, a hair dryer, so some kind of home appliance, you don't really think about the energy, if it's available or not, how it's being produced, how it's being delivered, and so on. You just simply would assume, okay, there is a plug, and I will have to, plug in the device, and I will be able to receive the energy. And this is something similar, right, that we would also like to have in this 3D continuum, so that we can consume the infrastructure as a utility, right? In addition to that, we would also want the applications to seamlessly move from the cloud to the edge and to the satellites, so that, depending essentially on their current needs in terms of latency, compute power, data access, and so on. And now the question becomes, is this already a reality? And unfortunately, the answer is obviously not yet, right? And it is not as simple as, just switching the plug. So consuming the infrastructure is not as simple as just switching the plug of an electrical appliance. So the question becomes, where are we right now, right? Where do we stand right now? And definitely we are not locked in a cage, so to say, and we have the choice to freely choose infrastructure and service provider. For example, Google, Microsoft, Fastly, Netlify, or whatever. However, once we have made this decision, we are largely locked in with this kind of, with the existing ecosystem that we have chosen. So I like to call this kind of, we have a limited freedom at home, right? Because we can use all the services which are offered by these providers, but then adding additional services and moving beyond that becomes very tricky. And ideally, what we would like to have is, we would really like to have this full freedom to run and execute applications without technical restrictions, so that we can efficiently manage the trade-offs, improve performance, reduce cost, optimize resource consumption, and really meet increasingly challenging demands of our modern society. So how can we effectively manage this new compute infrastructure by efficiently managing the non-functional trade-offs? And this is the question that we set to answer with the Polaris project. And essentially, Polaris is a joint venture between academia and industry, which is aiming to address such real life problems in 3D continuum. And it has been going on for several years, and since 2022, it has been hosted by the Linux Foundation. And next, I want to focus on two kind of mechanisms which are crucial for managing the compute continuum, which is the management of the SLOs and specifically the predictive monitoring. But before we start there, let's just quickly define what an SLO is, right? SLO, or service level objective, is a specific quantifiable target for the performance of an application, right? And what's important to note here is that SLOs can be measured, and also SLOs can be enforced, right? However, the traditional SLOs, such as the examples that you can see on your screen, they mainly focus on reactive low-level system metrics, which are typically unable to capture trade-offs in non-functional requirements, right? And this is the kind of our goal, which we want to achieve. And they're also very hard, again, typically to align with application business KPIs. So on the other hand, Polaris defines SLOs, which specifically focus on capturing this performance and reliability guarantees, and whose impact can be reflected in business requirements and KPIs. So, for example, instead of talking about CPU load, memory consumption, we want to talk in terms of high-level metrics such as cost efficiency, for example. And to achieve these high-level SLOs, Polaris SLO defines three main pillars, right? For monitoring, specifying, and enforcing the SLOs. And for monitoring, we define most notably the predictive monitoring capabilities, which I will talk about briefly. We also introduced a high-level SLO scripting language based on TypeScript, which enables us to kind of capture and specify these SLOs. And finally, we offer or we defined several enforcement mechanisms, right? And the enforcement mechanisms are the mechanisms which are required to mitigate or to enforce SLOs once they have an SLO violation happens. And there we have various techniques and various strategies such as serverless scaling, consolidation, scheduling of resources, and so on and so forth. And now, as I promised, I want to talk a little bit about this predictive monitoring. But before we do that, let's just make a distinction. What is a predictive versus reactive monitoring, right? And the reactive monitoring is the kind of more traditional way of monitoring, where you simply are observing a system and wait for an SLO violation to happen, right? So that you can detect it. And this can be, that your system is decreasing in terms of its cost effectiveness or whatever. And then only then after the SLO has been violated, we react in order to fix the problem, right? And with predictive monitoring, kind of we flip the narrative, and what we try to do is we try to predict these monitoring, the SLO violations, and then also try to preemptively react so that we prevent from the SLO violations from happening, right? And our predictive monitoring capabilities are based on two main prediction models, one based on the LSTM, so long short-term memory prediction models, and then the other one is based on temporal fusion transformers, or TFTs, right? And polarized prediction models, what is very interesting and specific is that they're designed so they can predict the high-level SLO violations, such as cost efficiency, given only the low-level infrastructure metrics. All right. So how our models fare, right? How do they perform? Well, we can see here that they are very capable, and this is an example of cost efficiency. They're very capable to predict the utilization or the efficiency, regardless, even if we look several steps in advance, so into the future. Right. And what's also important to note is that what this radar chart shows essentially that our training set, which is denoted in blue line, and the tests, I'm sorry, the training set is denoted in red line, and the test set is denoted in blue line. They are very different, which means that also our models are generalizing very well beyond, the specific metrics and infrastructure. Another aspect, or where we also applied our predictive monitoring is for the energy consumption. We saw already the importance of energy efficiency in computing. And to address some of these challenges, we developed several approaches to enable energy-aware SLOs. And here we see one of those approaches, right? Where what we essentially do is we are able to monitor the low-level sensory data such as CPU performance, I/O memory, and so on. And then we classify these into measurements, for example, counters and gauges. And then also after that, we split them into multiple time frames. So kind of we make a discrete signals, if you will, out of those. And finally, since this is working on the data center level, right? So the scale is really kind of large data centers with multiple hosts. What we do is we produce for each host a tree or a graph of these measurements and these metrics, and then we feed them into our GHT-GNN, which is the graph hierarchical transformer GNN, which in the end is able to produce or to produce the predicted energy consumption, right? And we have also then various other strategies, which we already kind of briefly mentioned, which enable us to essentially also manage the energy consumption in terms of scheduling and consolidation. And here we can briefly see the reduction or the energy saved, which is quite notable, again, on a data center level, and ranging from 1,300 kilowatt hours to all the way to 42,000 kilowatt hours, which are saved. Now, if we go further down this monitoring rabbit hole, we will find also a limitation of the predictive monitoring, right? So there are definitely limitations, and the problem which we are mainly facing here is that we are that we need to observe a workload before we can actually react to it, right? So we need, typically, the state of the art is that a workload or an application needs to be observed for 2 weeks before we are able to make some interesting predictions, right? And we address that with this metadata-based workload profiling. And I will just give you the main intuition here, since I'm now already running out of time. And the main intuition here is to use the a priori available metadata to derive some workload profiles and to conclude something about the workloads during their runtime. And here we can see some of the results which we were able to achieve. And the main takeaway is really that we can learn a lot about the future workload by looking at its metadata. Now we looked at how these kind of how we can use SLOs and predictive monitoring at the infrastructure level to manage these non-functional trade-offs. However, if you recall, we want to have the full freedom to run and execute the applications without any technical restrictions or with fewest possible technical restrictions. And to achieve that, in addition to these kind of innovations at the compute landscape level, we also need to look and re-examine the novel compute paradigms, right? And the very good news here is that a serverless computing can bring us kind of very, very close to what we are aiming at here. And this is mainly by offering these 4 core promises. One is that there is no infrastructure management, so simply you need to worry about your application without worrying about the infrastructure. The offer of flexible elastic scaling, so the applications kind of scale up and down based on the load without any intervention by the user. High availability, which is also offered out of the box, and probably most importantly, cost effectiveness, which is a result of this scale to zero property, which we'll discuss. Well, before we discuss that, let me just quickly, define serverless computing. And if you heard anything about serverless computing, you know that it does not mean that there are no servers, right? There are servers, but you as a developer or as an operator, you're not responsible for managing that. And this is also shown, right, on the figure here, as we can see that the number of these green boxes, which are kind of user managed, is significantly reducing in size as we go through this kind of evolution of cloud computing. And there are 2 kind of main aspects of this serverless computing. One is the novel programming paradigm, which is so-called function as a service programming paradigm, and also novel execution model. And quickly talking about the FAST paradigm, it is essentially a programming approach where we decompose the applications in a set of functions or actions and a set of triggers, right? And these triggers can be something as simple as uploading something in, let's say, an image into a bucket, and the actions are typically modeled by the functions, right, which implement this business logic. Each serverless function is deployed and executed within a dedicated virtual container. And there are various isolation and virtualization models, and I will not go into details here, but it's important to note that the container, so the container which hosts the function, is typically alive only during the request processing. And once the request processing is completed, it is scaled to zero, right? And here we see how this scale to zero architecture works. And essentially it boils down to when a request comes, there is no one service which is waiting for this request, right? Your application service, but there is kind of this ingress controller which waits for all the requests and then automatically loads the code and the functions from the database, instantiates it, passes the request to it, and manages that the response is returned, right? What's important to note here is that all of these steps 2 to 5 need to happen before the function gets invoked. So we can see that the scale to zero, one of the most important properties, comes at the cost of delayed start, right? Also known as a cold start issue. Hence, we see that we need to trade performance for cost efficiency. And serverless also goes beyond the FAS to also include this serverless bus. But I think it's more important to talk about many opportunities which are offered by serverless computing, such as fine-grained pay-per-use model, cost-efficient resource usage, again with scale to zero, rapid elasticity, and so on and so forth. So we can see really that there are many opportunities offered by the serverless paradigm. And if we can kind of now revisit all of these promises, the no infrastructure management, flexible elastic scaling, availability, and cost effectiveness, let's also see now how they fare or how they fare in face of various challenges, right? And there are several horror stories, which I like to call horror stories. One of them is the so-called runaway function. And what is a runaway function is essentially when your invocation, output of the function serves as an input to that same function, and you end up in this recursive loop, right, where the function invokes itself, and then you can instead of having better cost efficiency and reduced results, you can end up in situations like this. Another thing is that these serverless functions don't live in isolations, right? And we are dealing essentially with a complex ecosystem with broad implications on cost, performance, and reliability. But sometimes, if not managed properly, these trade-offs can go also in a different direction. So we can end up with being slower and more expensive, which is definitely not something that we desire. And then if we drill down a little bit more into the technical challenges, we can see, or I group these challenges in four main groups. Performance-related challenges, where we will be talking a little bit about the cold start, so like the function startup latency. We already discussed it briefly. Data management challenges, which is essentially sharing the intermediate ephemeral data in serverless workflow, so essentially transferring the data from one function to the other, or loading the data from some external state. But there are also other challenges, such as reliability engineering challenges, where we have to also deal with fault tolerance beyond simple retries, but also many software development challenges, which are definitely now beyond the scope of this talk. But I want to next briefly discuss how we deal with the problem of cold starts here. So how do we address this kind of cold startup, low latency caused by the cold startup? And the main intuition here is that we want to do some useful work while the function is starting, right? And this is as opposed to wasting compute and energy. And this is motivated by the image that you can see also on the right-hand side, where we see this kind of purple and turquoise colors dominating the function execution. And the purple one is the cold start itself, and the turquoise color represents the data transfer. And if you remember also from our initial discussion, these data transfers are something which is also very, very energy heavy, right? And our solution to this problem is introduced by Truffle, which essentially supports two modes. One is the state prefetching from storage, and the other one is the interfunction data passing, right? And here on the right-hand side, we can see how this interfunction data passing works. And if we just briefly look at kind of the details here, we have one source function which wants to communicate with one target function. And what happens there is that we also introduce our shim here, so our truffle shim, which sits between the function and the serverless platform, and it intercepts any kind of request to transfer the data from one function to the other. And then we kind of have these two execution parts, right? One is the function execution part denoted in black. So we have several steps which happen both on the application layer or level, but also on the serverless platform and orchestration platform. This would be, for example, Kubernetes. And all of these things need to happen before we can actually pass the data, before we can instantiate a function and pass the data to that function, right? And then we also have the other execution part or data prefetching part, which is denoted in blue. And what happens there is that the truffle, as soon as it gets kind of this request to send the data from one function to the other, what it does, it registers a listener in the API server. This would be, for example, API server from Kubernetes. And as soon as the scheduler determines where the next function will be scheduled, we are able to start transferring the data to that local buffer of that other function. So what it means is essentially that this data transfer can happen in parallel with all these steps 5, 6, 7, and 8. And this essentially leads to a very nice results, which I'm just summarizing here, where we can see that the overall latency, regardless of the communication, be it direct or through the storage, is much, much better by Truffle, so shown in blue, compared to the typical baseline, so working without the framework itself, right? However, addressing and exploring these cold starts alone does not really fully resolve the data transfer challenges, right? Regardless of the cold start, the data transfers to the function are particularly affected if we're talking about the stateless workflows, right? Because the functions themselves don't store the state locally, but they need to outsource the state somewhere, right? And typically, the overhead is introduced by two most important parts of communication, which is the data serialization and also data copying across user kernel or network spaces, which imposes significant overhead due to various context switching. So essentially syscalls that need to happen. And this is also depicted here. So if one function wants to communicate to another function, it needs to go through a series of these steps. And to address that, we also introduce another system, which is called the Roadrunner. And the Roadrunner defines these three modes of data transfer between serverless function, and it manages the function's memory essentially completely transparently via shims. And this is actually a very, very novel research which will be presented this week in Nashville, Tennessee at the Middleware Conference, which is one of the top tier conferences in our field. I will not go into all of these details, how all of these modes work, but I think if we just briefly look at this mode 2 or kernel space data transfer, it's interesting to notice there that so what happens there is essentially that we have this zero serialization approach with minimal copy enabled in the following way, right? The Roadrunner shims are sitting below the functions, right? And then when a function wants to invoke another function within the same host, the shim itself intercepts that and takes the data from that function, which needs to be copied to the other function. And what it does is it essentially allocates the memory within the user space of another function and proactively fills that memory space with the requested data, so that the function is then just simply notified by kernel in this case, or by our shim, that the data is ready. And this happens essentially it's completely serialization free because the data is just shifted and there is really minimal copying happening. So there is only just one essentially instance of copying happening, which is which has to happen because we are transferring it from one memory space to another memory space. However, we saw at the beginning of the talk that things are moving very fast in the 3D continuum, and more so they are moving along these perturbed Keplerian orbits. So loading function states can lead to extremely high latencies, right? And how this can happen, it's very simple, right? Imagine you have one function which is sitting on one satellite, and it needs to load its states from another, let's say, satellite which is residing currently on the opposite side of the Earth. So what we have to do is we have to either use this technique called the bent pipe, so that we can use the satellites to kind of transfer the state from one function to the other and use multiple hops essentially, which is then incurring long latency, or we have to go through the ground station or multiple ground stations, which then can typically incur 500 to 1500 milliseconds of end-to-end delays, even under ideal assumptions, right? And if the satellite is out of view or out of line of sight of the ground station, this can then go much and become much higher. So the main intuition here of the approach which we developed to counteract this challenge is essentially to propagate a function state to counteract orbital movements, right? So essentially you can view the state moving independently through the constellations, or even if you want to keep it, geostationary because you're doing some local computation, for example, observing an area for wildfire detection, this can be also kind of achieved or virtually achieved with this approach. And how data belt, this is the name of the approach, achieves that is essentially by breaking down the whole process into three parts. So identify, compute, and offload. And the most important, or the most interesting rather, part is the second one, the compute, where we are trying to select the most appropriate set of satellites and compute the shortest path to each one of them, right? And the whole idea here is to define these local groups, right, which are shown here in red. And what these local groups represent, they are kind of the groups of nodes, be it satellites or ground nodes, such as drones, clouds, data centers, and so on, which represent viable communication infrastructure in terms of the SLOs, right? But since there is a huge dynamicity that we deal with, we need to also not work just reactively, but we really need to predict which one of these nodes are likely to go out of range based on the orbital dynamics, for example. So essentially what DataBelt does, it constantly and continuously adapts this local group for different times t. So we said that this is now based on the orbital dynamics, but if we go further down this rabbit hole, there are multiple further constraints beyond orbital dynamics which need to be considered when dealing with data transfers and also scheduling in the satellite constellations. And these involve, for example, thermal management, because satellites are frequently exposed to solar radiation, obviously because they're orbiting the Earth and they're facing the sun, at least during some time or some portion of that orbit. And the temperature fluctuations are really, really high, ranging from negative 120 Celsius all the way to positive or plus 120 Celsius when the satellites are in shadow or in the sunlight. And the problems are even more exacerbated because of the heat dissipation is only possible via radiation. So there is no way to conduct that away from the satellites, obviously, but also the convection is not possible because we are mainly in either extremely thin atmosphere or in a vacuum, so to say. And then another also interesting aspect which needs to be considered is the energy capacity, because the satellites are usually solar powered, and what this means is, right, they recharge in the sunlight and then deplete while they're in the shadows, and executing function. Scheduling and executing the functions needs to be mindful of these limitations so that we do not deplete the battery. And all of this and much more we discuss also in one of our relatively recent publications, Hyperdrive. All right, so with this, I'm coming to an end of this lecture. And to conclude the talk, I have three main takeaway points, right? First of all, I wanted to convince you that we are dealing with the 3D compute continuum as the next generation of compute infrastructures, right? And it is not just a cloud anymore. We are definitely moving, or have started moving beyond that. And unlocking these features of the 3D continuum brings us numerous benefits, but it also requires us to solve novel research challenges that we have seen, discussed, and partly also showed some of the solutions to that, right? And I try to discuss the most important aspects today. Secondly, we saw that serverless computing brings many opportunities when building and managing applications in terms of improved reliability, reduced costs, and also no infrastructure management. But again, also in this context, we need to deal with novel challenges to fully unlock the capabilities of this 3D continuum. Yes. And then finally, by combining these two novel paradigms, we can enable the applications or the systems of the future to get closer to effectively managing the trade-offs between performance, scalability, reliability, and also cost efficiency to sustainably respond to the computing demands of our society. And with this, I would like to thank you for your attention. And if there are any questions, I would be more than happy to answer that. And yes, I saw that. I think this is the only slide, Katie, where where I have the
Alles
output.
good. Very good. Very good. Thank you very much, Stefan. It's really interesting. So far, I always thought the satellites are just for our, colleagues from geoscience and geoinformation who are dealing with flood prediction and earthquake prediction. But it's really very interesting to, as you presented the whole way down, how you use it also for the compute continuum. So, I'll look also in the chat if there are any questions from the other colleagues in the. I would have a question concerning the real costs. The satellites are to a certain extent publicly owned, but they also, of course, they're private ones. Do you have any estimation how much the kind of, also the euros or the dollars, how much the costs are? Is there a change in the cost model and the cost structure?
That's a very good question, and especially because the largest cost item is essentially launching of the satellite, and now just one satellite, not the whole constellation, right? And this can really this is typically priced based on the kilograms of the payload which are launched, and for average kind of LEO satellites or these kind of smaller size scale satellites, we can go all the way from let's say some 5,000 to 8,000 euros all the way to 30,000 euros to perform the launch. So it can be quite costly, right? And this is why I also mentioned that this is one of the trade-offs, right, which we need to take into account. But specifically here, the idea is that what we have seen emerging is these kind of novel constellations as a compute platforms, which will hopefully in the near future be open to third parties, similar how the cloud became open to third parties. And we already see this, albeit not as in a fully utility-based consumption model, right? So this is why we still don't have this compute freedom, this complete freedom to compute everywhere. However, there are already startups and companies which offer essentially leasing, if you will, a satellite, and then putting your computation there and executing some computation, which is then significantly smaller, cheaper compared to building your own satellite, launching it, putting it out in the orbit, because as we said, it can go up to tens of thousands of dollars or euros to do that.
And do you have an idea how much computation already takes place in this 3D continuum?
Well, how we view the 3D continuum, right? It's the combination of this edge cloud continuum, which is kind of residing at on the Earth, and then you have this kind of third spatial dimension, which is offered by the satellites. And I would argue that a lot of the world computation, probably vast majority actually of the world computation, is happening currently in the 3D continuum. And one of the ways how I can kind of substantiate that is if we remember, this year alone we had, I think, 3 or 4 outages of various platform providers like AWS, that was, and recently we had also Cloudflare and so on. And once that happens, we see many infrastructure components, but also many applications just being completely rendered useless, right? You cannot even log into your email, you cannot call Uber, you cannot access Netflix if that's one of the key services which is needed. So I think that since the definition of this 3D continuum is very broad, also the amount of computation which happens in it is very, very large. And it's kind of that is also one of the main premises which I have for my research, is that almost all or many of the critical infrastructures are dependent in one way or another on this distributed computation within the 3D continuum.
Mhm.
And it is just increasing, if I may add. It is just increasing, specifically also now with with this kind of in-orbit computing gaining traction and increasing in importance for not only communication but also being able to do remote computation near some previously geographically inaccessible areas. Also, coordinating autonomous vehicles, also coordinating UAVs and so on. I think we're just poised to kind of see an exponential increase also in the future.
Wow, interesting. um, I don't. I have to look at the chat again.
I can also.
Uh, I don't think that there are no further questions. Just then a last one from mine, and I'm really a totally layperson in this area. Uh, More and more also this kind of space waste is a topic, not like what about if, the satellites don't work anymore and so on. Are there any is there any research, or are there any considerations what to do with, how to renew the satellite infrastructure then?
That's again a very good question, and especially from the perspective of sustainability, this is, I think, the most challenging aspect of this
Mhm,
in-orbit computing. Now, I also have to kind of distance myself a little bit from this, because we are not building satellites, as you obviously
mhm,
know, and we are not launching them, we are not managing them. We are kind of trying to exploit them as a compute nodes. But I recently listened to a webinar from it was from ESA, FFG, and then also Swiss National Space
Science
Agency.
Foundation, okay.
And basically, their main focus is dealing with the debris of satellites in the future. So what happens is essentially, right? I
Okay.
mean, it's a big deal, right? Because you
Yeah.
have now just as we mentioned that Starlink has they're planning to have up to 20,000 of satellites and that's just one company, right? And then there is AWS with Kuiper Belt. There are also national agencies and so on and so forth. And currently, the strategy is when the satellite reaches end of life, it simply remains there, right? It simply remains there as space debris and continues just orbiting essentially as trash, right? Which is bad for many reasons, obviously, because it's not sustainable, it pollutes, and also it is kind of it is problematic for the evolution of the infrastructure, because
Mhm,
these debris then collide with the proper working satellites, and then they can kick them out of their orbit or whatever, and it's very easy to then just multiply this trash, so to say, in space. So definitely the space agencies are taking this seriously. Again, this is not something which we are focusing on, but people are taking this seriously, and this is one of the probably most urgent challenges now related to the general in orbit computation. Very good question, yes.
okay. Well, spooky, you know. So I stopped asking questions, otherwise it's getting more and more spooky. Stefan, thank you very much. It was a really very, very interesting, a totally new dimension of an insight in sustainable computing. Thank you to the participants. This was our last lecture before Christmas. I wish you all Merry Christmas, a Happy New Year, and we see each other on the 12th of January. I have seen Andreas Uhl, I think he was one of the participants, and then he will be our presenter in the first of the first presentation in the new year. So thank you very much to all of you, and goodbye.
Thank you for having me.
Bye.
Bye-bye.
Thank you, Stefan.